Good morning, everyone. Today, I want to tell you a bit about how vision can enhance GNSS applications. We heard some great stories this morning about the implementation of autonomous robots and the benefits of using GPS. We also heard from Septemtrio about the importance of resilience of GNSS. GNSS is one of the best technologies out there for scalability. It's very precise. You can get down to centimeter accuracy with RTK-GNSS. It's available. You get global position and orientation, and you get that directly. And it's very scalable. It's low cost, it's computationally efficient, and it doesn't require mapping or anything. So from the get-go, you have a precise solution that tells you where you are at all times. Vision, or visual inertial odometry, has other benefits. It's robust, so you can navigate indoors, you can navigate through urban canyons, you can navigate in dense forests, through orchards, and you always have a good pose. You get real-time high frequency and low latency pose estimates, which is one of the shortcomings with GNSS. And it's self-contained. It doesn't require any external infrastructure, any beacons, any satellites, or anything of the sort. But both of these technologies have their own shortcomings. GNSS, while it's great in open environments when you have good satellite visibility and good corrections, um, it can have issues with signal interference, with obstruction. Um, in certain environments, you see that it has very limited accuracy in urban canyons, in orchards, close to buildings, and even in areas where you might have um, poor coverage of either RTK correction services or um, or a 4G cellular network to receive those corrections. So it requires the corrections, and that's one of the weaknesses. And it does depend on external signals. So as soon as you're going indoors, it's not very useful. VIO also has its shortcomings. I mean, there's a limited operational range, and drift accumulates. So you have errors over time. Of course, you can handle this with mapping, but it's computationally more complex. It can take a lot of resources. And in addition to that, maps can change. So when you're navigating outdoors in environments that are very open and you don't really have features to track, or in environments that are changing a lot, this can be in agriculture because from one day to the next, an orchard has had all its fruit picked, or because it suddenly snowed. There are challenges, and there are challenges with initialization and relocalization. So how do we overcome these challenges? Well, we at Fixposition are focused on a number of things. We are GNSS experts, we have um, vision experts, and most importantly, we do fusion. So we harness the strengths of different technologies, we take that raw data, and we combine it into our X-Fusion engine. And this allows us to provide a very reliable position and orientation. We take in raw RTK-GNSS data, we take in raw IMU data, and we take in raw tracked features from our visual odometry front end. We can also add in other sensors where necessary, for example, a vehicle speed estimate either through wheels, through radar, or anything of the sort. And we leverage all these different sources of information to overcome respective weaknesses. So how exactly does our fusion work? Kalman filters are typically the most standard solution out there. However, Kalman filters have issues. One of them, for example, being uh, the fact that it's less scalable due to large-scale problems with EKFs. They don't handle nonlinearity very well. Um, they will struggle if your environment is changing a lot. I mean, the dynamics of the environment or of the platform. So it can be overly focused on the tuned environment and vehicle, and it's less robust. What the benefits of the factor graph are that we have a probabilistic model that represents a lot of variables and measurements in a whole system. And these variables allow us to very accurately, over multiple states, um, keep live information about where we are and where we're going. So by having this closed loop function in our factor graphs, we're able to correct errors, re-optimize for past states that are still open. And that means we can correct errors retroactively, improving our overall accuracy. It also ensures consistency in the estimation approach, as new measurements can refine the entire trajectory, not just the current state. So our optimization approach ensures this consistency and increases the stability with a fixed complexity. So how do we do this, and what exactly is powering the X-sens Vision Navigator? Well, in the X-sens Vision Navigator, we have a number of sensors already embedded. This includes a camera, IMU, two GNSS receivers, and we have a positioning engine. Now, our positioning engine is able to run on this low-end compute system, which is a challenge, and run this in real time to give world-class performance in terms of pose and velocity estimation. Um, so the XVN is one of the best solutions on the market to use in environments where dead reckoning is necessary, where GNSS alone might not be helpful, where mapping might be complex, or where you might be um, navigating between environments where you can map certain indoor areas, but outdoor ones might become too complex or are changing too rapidly, or even if you need some redundancy there. But in practice, getting such an optimization to work well is very complicated. So we need to train our algorithms to be able to adapt to the environments and platforms on which they're being used. Now, the XVN doesn't automatically record any data, but customers that have challenges in different environments, they are able to record the data, share it with us, and we can train our algorithms and redeploy that to all our customers to improve these corner cases and ensure best-in-class performance in a variety of environments and a variety of platforms. So these platforms will include platforms in urban settings such as delivery robots, street sweepers. They will include tractors that are navigating through orchards, lawnmowers. There are a multitude of applications here. So how exactly does this retraining of the model and deployment help? Well, it helps us, and we heard about this challenge earlier with Septentrio, identify spoofing and reject bad GNSS. We're also able to identify false fixes, and this is one of the things that Septentrio was correctly pointing out, is that sometimes you can have measurements that are inaccurate, but they tell you they're very accurate. So when I talk about a false fix in the sense of RTK-GNSS, I'm talking about an RTK fix where our GNSS receiver tells us it's certain of its position down to 2 centimeter accuracy, and actually it's maybe 1, 2, 3 meters to the side. So thanks to our complex models and these different sensors embedded, we are able to identify these measurements, reject them, and adjust our covariances as a result. Our optimization problem actually contains hundreds of parameters. So when I talked about um, this factor graph optimization, you hear a lot of academic papers in deploying this, and it can work well in certain settings. And for academic purposes, you will have a specific example where it works really well. But deploying this into a product in the real world, where platforms change, environments change, where they're confronted to um, different issues with measurements, whether it's from the camera having interference, from um, objects moving in front of it, whether it's GNSS having interference, is very complex, as well as I mentioned the dynamics of the platform or um, changes in the environment. So these hundreds of parameters allow us to represent different models for these changing vehicle dynamics, environments, and much more. We're able to improve this with our machine learning training methods and have models that allow the parameters to self-tune dynamically in real time when necessary. What does that mean? That means unlike a standard application where you choose one tuning mode and your vehicle is using that, we've developed complex models that represent underlying use cases. And within those models, we have self-tuning parameters that might adapt in real time. So for example, if you have a vehicle that at one moment is driving at 2 meters per second and later will be driving at 20 meters per second, some of those parameters will adapt because the way uh, the vision and parallax is changing is going to need to be handled differently. We also have different time to do computation in those scenarios. The IMU dynamics might be different. So we have developed very precise models to represent this. And this has given us the ability to refine this. We've collected tens of thousands of kilometers of data from all over the world, from various different locations, environments, use cases. And this has allowed us to outperform classical rule-based approaches by more than 70%. So what does that look like when we look at some statistics? And why should you choose the XVN over a standard high-end GNSS INS solution? Well, here we look at the error as a percent of distance traveled of a standard high-end RTK INS system. This is representative of a $20,000 high-end RTK-INSS system. It's very useful in certain circumstances, but here we took data from about 800 kilometers of randomly selected data sets with ground truth, and we looked at the errors in areas where GNSS had outages. And we considered GNSS outages anywhere where GNSS was no longer useful for the dead reckoning. We had to rely almost purely on VIO or INS solutions, because if you have bad GNSS 3D or RTK float GNSS, you might have GNSS that's only accurate from 5 to 20 meters, and that doesn't help if you're trying to maintain centimeter accuracy. Now, this data is compared to the post-processing of the high-end RTK-INS solution. So here we're looking at the percent of error as a percent of distance traveled of the high-end solution against its own post-process result, and the same for the XVN. So the XVN is compared to the post-process result that was used as the ground truth, and it's the post-process high-end and not the XVN's result. So there's a tad skew to benefit the high-end system in this case. So in an outage, what's the probability of your error being less than 1%? Well, in most cases with the high-end solution, it's close to 25%. With the XVN, we're already looking at a close to 80% probability. Having an error below 2%, with the XVN, we're looking at a close to 95% probability. And below 5% with the XVN, you're almost certain in all types of outages to have that reliability. If we look at the metrics in terms of mean, median, and standard deviation, we see a significant difference. Um, the mean of the XVN is well below 1% of distance traveled, and more importantly, the standard deviation is also well below 1% versus high-end solutions that can have the high 6 to 10, 20% errors. More than that, the XVN doesn't suffer from time-dependent drift as a typical INS system would, thanks to the use of the vision to identify when it's moving slowly, when it's stopped, and it only accumulates drift with distance traveled. So I want to take you through an example last week of our colleagues driving through an urban canyon in China and what that looks like. Here we can see on the left side of the image what the camera sees. You have a lot of traffic moving around, you have cars, vehicles. On the right, you'll see the XVN performance and you'll see the RTK GNSS. So we just went into a tunnel, the GNSS completely disappeared, there's no more signal, you have nothing at all. All of a sudden, the GNSS comes back, but it's 20, 30, 40 meters away. Even here, we're still between canyons, the reception is still bad, the GNSS performance is still at the 10-meter level, 3-meter level, and only once you get to open, it rejoins the XVN's position down to uh, centimeter level accuracy. So just to highlight what this exactly means, here we have an example of a typical drive um, in an urban canyon in China, where you go through tunnels, you go through a number of areas where there's just no GNSS or you have a lot of multipath. And you can see that you have huge gaps of no position and you have a lot of areas where your position accuracy is at best 10 meters accurate. The XVN allows you to maintain high centimeter accuracy throughout those areas, and this includes these heavy multipath regions. To give you a bit more insight, if you look at the area on the right, you see a lot of multipath. You see the XVN performance. If we zoom in and just give an example of this, we can see that over a 1 kilometer example of multipath where the vehicle turned around, came back, you see when it rejoined on the left, the RTK fix, the XVN was still centimeter accurate, whereas the GPS in this situation was accurate on average 4 to 5 meters throughout this trajectory. What about other use cases? Because as I mentioned earlier, the XVN is used not only in urban canyons, not only in cities, but also in other applications such as agriculture. Well, we heard earlier this morning about the benefits of agriculture and um, some of the use cases and how you can do row detection to maintain your position in the row. But it can still be a challenge if you're navigating through orchards where your position is way off that might show that you're 1, 2, 3 rows away and you don't know where you are. On the left, you'll see this is data we collected a couple of months ago in the US in some dense walnut orchards. And you can see on the left that the GPS alone really struggled. And in fact, at times it was 2, 3 rows away. So the system had no idea where it was. And on the right, you can see the XVN was able to maintain really accurate positioning throughout, enabling better control, better performance, and increasing the operational viability for these types of applications and for our customers. So by providing this reliable and accurate GNSS or position at all times, our customers are able to significantly simplify the control problem and really focus on deploying and getting to market quickly.